Hi, this is Mr. Mac. Today, we are going to talk about imaginary numbers. Imaginary numbers now are a concept or idea whose time has come. We need imaginary numbers because some of the equations, some of the very simple equations we're going to be dealing with that are quadratic equations, don't have solutions if we're dealing with real numbers. And we've seen that already. We've had quadratic functions whose graphs are parabolas, and the vertex is above the x-axis, and they open up, so the parabola does not cross the x-axis. And what you were taught to write was no real solutions. Well, that's not good enough. So we're going to actually work on expanding our number system so that those kind of equations do have solutions. And the way we do that is we define imaginary numbers, or the imaginary unit. So first of all, let's start with a definition. We're going to define the square root of -1 to be equal to the imaginary unit I. Now, a couple of things I'd like to point out. This imaginary unit, the square root of -1, is not real. Okay, now when I say it's not real, I mean it's not a real number. I am not talking about fairies and pixie dust and things like this. This is an actual mathematical idea. It has actual applications. You will need to be able to deal with this, not just in math class, but in many of your classes in science and technology, and so this is very important. So don't develop an attitude because of the names. The name sometimes might be a little unfortunate, imaginary, but it is an actual mathematical idea. Okay, now that's kind of reinforced by my saying it's not real. But what I mean by that is if you take a positive real number and multiply it by itself, another positive real number, you will get a positive real number. Now, if you take a negative real number and you multiply it by itself, another negative real number, you'll get a positive real number. If you take 0 and multiply it by itself, 0, you'll get 0, which is, well, it's not positive, but it's not negative either. So anytime you square a real number, you're going to get a number that is either 0 or positive. Now, by the very definition, if I is the square root of -1, and I've always felt that that was grammatically incorrect. Should we be saying I am the square root of -1? No, not really. We will say if I is the square root of -1, when we square I, in other words, if we square the square root of -1, and this number is defined to be the number that when you square it, gives you -1, in other words, the number that's inside the radical. If we square that, we should get -1. Now, since any real number squared is either going to be positive or 0, and if we square this number, we get -1, then the square root of -1 is not in the set of real numbers. So it's a new number, it's outside the set of real numbers, and we call it imaginary. Basically, it's a play on words mathematicians came up with because it is not a real number. What would you call it? Well, they called it an imaginary number, but it is actually a number. All right, now we have now what you would call a definition for the imaginary numbers, and there are lots of them. We can have many pure imaginary numbers, and it works like this. A pure imaginary number is any number of the form AI, where A is a real number. So in other words, we could have examples I, 3I, negative 7I, pi I. Any number times I is a pure imaginary number. Now this isn't enough even for us. We want to kind of match this up with the real numbers if we can. So we take the imaginary numbers, the pure imaginary numbers, and we add them to the real numbers, and we get what is called a complex number. Now a complex number is any number in the form a plus bi, where a and b are real numbers, and of course I is our definition, the square root of -1. Now, we're going to talk today about how to deal with these complex numbers mathematically. The first thing I would like to point out is that when you have a negative sign under a square root, for example, if we say the square root of -4, this is really the same thing as the square root of -1 times the square root of 4. We're allowed to split a radical up through a multiplication sign, and we know that the square root of -1 is I by definition, and the square root of 4 is 2, so we get 2I. Now, what I tell students to do is that whenever you get to a radical that has a negative underneath it, you need to deal with that negative sign first. And if it's a square root, what happens is this negative sign comes out as an I. So an easy way to remember this is to always pluck your eyes out first. Now this even becomes an order of operation. In other words, if you don't do this first, you can end up with a problem. Let's see if I can illustrate this. Let's say, for example, I have the square root of -12 times the square root of -3. Now, our new order of operations is to pluck your eyes out first. And notice we have a negative sign inside this radical, and we have a negative sign in this radical. So this becomes I times the square root of 12 times I times the square root of 3. Now, if you don't do that first, I'll show you what happens in a minute. Now, this becomes, now remember here, this is multiplication right there, and this is multiplication right there. So we can write this as I times square root 12 times square root 3. I times I is I squared. Square root of 12 times square root of 3 can be thought of as square root 36. Now I squared is the square of the square root of -1, so we get -1. And the square root of 36 is 6, so we get -6 for our answer. And that's the right answer. The square root of -12 times the square root of -3 is -6. Now, I almost hesitate to actually even do this because if you see this, I'm afraid you may say, well, I'll do it that way. And this, what I'm about to show you is wrong. Now, I'm going to write it in red, and then I'm going to put a big red X through it afterwards. What you're about to see is wrong, and what I'm doing is I'm trying to illustrate the mistake you can make if you don't pluck your eyes out first. So let's go back. Square root -12 times square root -3. If you just said that is the square root of -12 times -3, that becomes the square root of +36, which becomes 6. Now, in this case, 6 is referred to by all mathematicians as the wrong answer. And why is it the wrong answer? Because you didn't follow the order of operations, which we've kind of modified now to say, pluck your eyes out first. And you did not pluck your eyes out first. And therefore, this is wrong. So remember, as you go through complex numbers, pluck your i's out first. Now, the next thing in dealing with i's mathematically is we would want to know what different powers of I are. Now, I to the 0, of course, is going to be 1 because we know everything to the 0 is 1, and that works with i's too. I to the 1 is, of course, I. Now, I squared is negative 1. We've kind of gone through that already. If I is the square root of negative 1, when we square the square root of negative 1, we get negative 1. Now, I cubed is, by our laws of exponents, could be thought of as I squared times I. But I squared is negative 1. And negative 1 times I gives us negative I. So I cubed is negative I. Now, I to the 4th could be thought of as I squared times I squared. Now, I squared is negative 1, and I squared again is negative 1, and negative 1 times negative 1 is 1. So I to the 4th is positive 1. Now, something strange happens. I to the 5th could be thought of as I to the 4th, 4 to the I to the 4th times I to the 1. Now, by what we just saw above, I to the 4th could be thought of as 1. So 1 times I to the 1 is I. I to the 6th could be thought of as I to the 4th times I squared. And we know I to the 4th is 1, and we know I squared is negative 1. So we have 1 times negative 1, which gives us negative 1. Now, if you think about it, I to the 7th, well, we maybe should do a couple more. I to the 7th is 7 to the 7th? I don't know what's going on here. Okay. I to the 7th could be thought of as I to the 4th times I to the 3rd, because remember, when you're multiplying exponents and you have the same base, you add the exponents. So 4 plus 3 is 7. Now that's 1. I to the 4th is 1, and I to the 3rd, we've discovered, is negative I, so we get negative I. So we get 1 times negative I, or negative I. Now I to the 8th, I to the 4th times I to the 4th, 1 times 1, or 1. And look what's happening here. 1I, negative 1, negative I. 1I, negative 1, negative I. And then I to the 8th was 1. We get this rotation that goes, it just goes around and around, and it repeats itself every 4 units. So what happens is, if you have an I to a fairly large number, let's say we have I to the 147th. 147 divided by 4 is, 3, 12, 27, 6, 24. So remainder 3. So I to the 147th, you could think of this as I to the 144th times I to the 3rd. But I to the 144th is just I to the 36th raised to the 4th power times I to the 3rd. But, no, let's go back. Instead of I to the 36th raised to the 4th power, let's think of this as I to the 4th raised to the 36th power. I to the 4th raised to the 36th power times I to the 3rd. There we go. So what we've got is we've got 36 I to the 4th. So that's how many 4s are there in 147? Well, there's 36 with 3 left over. So we have 36 I to the 4ths times I to the 3rd. But what was I to the 4th? I to the 4th was just 1. And 1 raised to the 36th power is still just 1. So we get I to the 3rd, which is negative I. But the key here is what you can do if you have I to a large power is if you divide the power by 4, throw this part away and just take the remainder. That will be the same thing. So then all you really have to remember is what I to the 0 is, I to the 1, I to the 2, I to the 3 and I to the 4, and you'll do just fine. All right, so powers of I. Now, the next thing we'd like to take a look at is how do you deal mathematically with complex numbers in adding, subtracting, multiplying, and dividing. Okay, first of all, let's talk about adding complex numbers. Well, if you have 2 plus 3i, that's a complex number, and you want to add it to 5 minus 4i, what you're going to do is you're going to add the real parts together. 2 plus 5 is 7, and you're going to add the imaginary parts together. 3i minus 4i is negative I. So the sum of 2 plus 3i and 5 minus 4i is 7 minus I. If you're subtracting complex numbers, let's subtract these two. 2 plus 3i minus 5 minus 4i. You simply distribute this negative sign over the complex number you're subtracting, so it becomes 2 plus 3i minus 5 plus 4i, and then you add the real parts. 2 plus negative 5 is negative 3, and the imaginary parts, 3i plus 4i, is 7i. And so when you want to subtract 5 minus 4i from 2 plus 3i, you get negative 3 plus 7i. I'm sure you're going to get plenty of chance to practice that. Okay, now, multiplying complex numbers. Let's say you have 5 plus 4i, and you wish to multiply that by 3 plus 7i. Now, this looks an awful lot like two binomials being multiplied together, and it behaves exactly the same way, except for one thing. Now, watch out for this one thing, okay? So let's start out. If we're going to multiply these complex numbers together, we are going to FOIL them. First, 5 times 3 is 15. Outer, 5 times 7i is 35i. Inner, 4i times 3 is 12i. And last, 4i times 7i is 28i squared. Now here's the part that you have to watch out for. I squared is defined to be negative 1. So 28i squared is negative 28. Now 15 plus negative 28 is negative 13. 35i plus 12i is 47i. Now, guys, you got to listen to me here. If you stop at 15 plus 47i plus 28i squared, I will not give you any credit. You must know and recognize that I squared is negative 1, and when you see it, you must replace it with negative 1 and continue on until you get an answer. It is not acceptable to leave it as I squared. All right. Now, division requires a little bit of talk. Now, first of all, I'm going to define for you complex conjugates. Complex conjugates are two real numbers of the form a plus bi and two complex numbers of the form a plus bi and a minus bi. Now, notice what happens is we have the same two complex numbers, except the sign of the imaginary part is opposite. Now, complex conjugates are special. 2 plus 3i's complex conjugate is 2 minus 3i. 2 minus 3i's complex conjugate is 2 plus 3i. They are complex conjugates of each other. Now, if you multiply complex conjugates together, you will get a real number. In other words, 2 plus 3i times 2 minus 3i. When you FOIL this out, you get 2 times 2, which is 4, 2 times negative 3i, which is negative 6i, 3i times 2, which is positive 6i, And 3i times negative 3i, which is negative 9i squared. Now, I squared is negative 1, so this whole thing becomes positive 9. Negative 9 times negative 1 is 9. Now, 4 plus 9 is 13. Negative 6i plus positive 6i is 0. So 2 plus 3i times 2 minus 3i is 13. Real number for the answer there. And mathematically, that's very special. Now, let's take a look. Generally, a plus bi times a minus bi becomes first a squared, outer negative abi, inner positive abi, and last negative b squared I squared. Now, negative abi and positive abi cancel each other out. And I squared being negative 1, we end up with a squared plus b squared. Now, this is always true of complex conjugates. And if you remember this, this will enable you to look at something like this multiplication problem here and know the answer very quickly, because the answer to this is just 2 squared, that's 4, plus 3 squared, that's 9. Now remember, the answer we got was 13. Ask yourself, what is 4 plus 9? Well, it's 13. So when you're multiplying complex conjugates together, you get a real number. Now that's going to be very important, because one of the things that we're going to want to do is we're going to want to divide. So let's say, for example, I have 5 minus I over 3 plus 4i. And I want to divide 5 minus I by 3 plus 4i. Now, guys, mathematically, it's not going to be right to leave any imaginary number or any complex number in the denominator. Those denominators have to be made real. Now, there's a really horrible joke here. I'm going to tell it to you. Remember back in geometry or early algebra 2 or algebra 1, when you had something like 1 divided by the square root of 2, you were told, well, you can't have a square root in the denominator, so you were taught to multiply by the square root of the denominator, the denominator over itself, which gave you square root of 2 on the top, and square root 2 times square root 2, of course, was 2. And this was called rationalizing the denominator. Or in other words, we're making the denominator rational. Well, now what we want to do in this case over here is we want to make the denominator a real number. So I'm going to call this realizing the denominator. Nobody else does, but I do. So we're going to call this realizing the denominator. Now, the way we're going to do it is we're going to multiply this fraction by 1, just like over here. We multiplied this by 1. We're going to multiply this by 1. Now, the form of 1 that we use is going to be the complex conjugate of the denominator over itself. In other words, 3 minus 4i over 3 minus 4i. Now, guys, if you want to, it's fine with me for you to FOIL out the denominators. But if you've been paying attention, you should know that the denominator is going to be 25. How did I get that? 3 squared, 9, plus 4 squared, 16. 9 plus 16 is 25. Now go ahead and FOIL it out if you don't believe it. Keep FOILing it out until you do believe it. And after that, you can kind of, when you've got complex conjugates and you're multiplying, you square the first number, square the second number, add them together. Now, in the numerator, you do have to FOIL those. So 5 times 3 is 15. 5 times negative 4i is negative 20i. Negative I times 3 is negative 3i. And negative I times negative 4i is positive 4i squared. Now, this is going to be negative 4. So 15 minus 4 is 11, minus 23i all over 25 would be the answer we get when we divide 5 minus I by 3 plus 4i. Okay, so in the video here, we've taken care of adding complex numbers, subtracting complex numbers, multiplying complex numbers, dividing complex numbers, powers of I, and realizing the denominator. Now, Why do we need this? Well, one of the things that we're going to have is we're going to have to solve quadratic equations. Let's just start out with something really simple. How about if our quadratic equation is x squared equals -4? Now, one of the things that we can do to solve a simple quadratic equation like this is to take the square root of both sides. When we take the square root of both sides, on the left-hand side, the square root of x squared is x. On the right-hand side, we get the square root of -4. Now, one thing I am going to mention right here, because I don't know when this might have been I can do this. I don't know where this would have been mentioned before. But when you take the square root of both sides, you must put in a plus or minus on one side or the other. It's extremely important, and if you don't, a lot of times you're going to get the wrong answer. So what we've got here is the square root of x squared is equal to plus or minus the square root of -4. So we get plus or minus over here. Now, negative sign inside the radical, we pluck our I out, it becomes I, and then the square root of 4 is 2. So x equals plus or minus 2i. Positive 2i and negative 2i. Now, we need to be able to take the square roots of negative numbers so that we can solve equations using the square root principle or the square root property. And so therefore, here it is. Now, let's a couple of examples. What if I have x squared equals -27? Then to take the square root of both sides, I get x is equal to plus or minus the square root of -27. So x is equal to plus or minus I times the square root of 27. Notice here the negative sign comes out as an I. I plucked my I out. Now, we can't really stop here. Are there any factors of 27 that are a perfect square? Why, yes, you say. 9 is a factor of 27, and it's a perfect square. So we have to think of this as x equals plus or minus I square root 9 times square root 3, and then we can take the square root of 9, so x is equal to plus or minus 3i square root 3. And that's the square root principle. So in this particular section, if you're solving a quadratic equation algebraically, they want you to use the square root principle. And we're done.